There's the recording. Can everyone see the recording and everyone see the slides? Shout in the chat if you can't. Brilliant. So I'm going to be the main one giving this introductory lecture. The course, as I said, is new. It's an 8-week course, but we're going to be mainly focused on our teaching for the first 5 weeks, and then we're going to use guest lectures. And I'm going to try and give you a bit of a sense of the philosophy about how we decided to pull this together. And part of the way I'm going to do that is by showing you this slide, which is just a YouTube link to the NYU Deep Learning course. And this is a 15-week course, so it's longer than ours. And it's taught by Jan LeCun. And the reason I wanted to sort of share this with you is to highlight that there's an enormous amount of material available to learn about deep learning and how to do deep learning. And Jan is, of course, a Turing Award winner and one of the originators of the convolutional neural network, has been doing this for years. So he's got a wealth of experience, and you can watch him give these lectures. And if I were to click play, that's what we would see now. And we've talked about this, and we decided we don't want to just do a bad version of what Jan would do for you, because you can see Jan doing the Jan version of what he does. So that's a course given by Alfredo Canziani and Mark Goldstein. And I'd urge you to look at those courses and other things online. There's so many resources for deep neural networks that will give you all sorts of insights. So what does that mean for us? Well, here's the three of us. We have different expertise, as you've just heard. So Ferenc, actually, his startup was acquired by Twitter, and the core product of that startup was a deep learning algorithm for compressing images, well, videos, that Twitter now use as part of their production of videos. It was a vital product for Twitter, as I remember, for Twitter to do some of their broadcast work on the Super Bowl. So he's not only developed deep learning models, he's sold companies which had those deep learning models involved. It's super exciting to have Nick, of course, because so much of what you're going to hear from me today is not about the methods themselves, the machine learning algorithmics in terms of why deep learning is popular now, but to do with the hardware availability and the data availability. And Nick's expertise in understanding how these map onto the hardware is another totally crucial part. I'm, in some sense, just going to be providing context and be giving the first lecture on generalization and sort of pulling the thing together. But you know, what we're aiming to do is not to provide you with a comprehensive course on every neural network that you can run, but give you the contextual understanding of why these things work, the sort of things you need to look at, and the sort of things, the pitfalls you need to avoid. Great. So on that, and the schedule's up online. There's a website which is the ml@cl.github.io/deepnn that hopefully you've all found, which shows the schedule. And in fact, I might switch to that website in a moment, just to also show you how my lectures will be done, which is the slides will be up there and the notes will be alongside. So let's just see if you can see that. So this is on the Deep Neural Networks, the course website. So this is today's lecture, and I've provided you with the slides, and I'm also providing you with notes. So all those links on there available, and this is the piece we're up to at the moment. So if you want to follow by having that open beside you, you're quite welcome to. And if you go to the sort of index page of the DNN section, you will also get presented with, as it says, draft, because I mean, I think it's pretty much not draft now. This is what we intend to do, what each of the different sessions are going to be about. Okay, but just to sort of review that on the slides. So this is week 1, and I'm just giving you the introduction, and I'm going to emphasize the importance of data in machine learning. And then on Tuesday, I'm going to talk a little bit about one of the things I think is most interesting about this new wave of models, which is different ways of thinking about generalization in those models and how that compares to our classical way of thinking about generalization. So generalization being the ability of the model to predict well out of sample, out of training data. And apparently I can't spell lecturer, but I'm still a lecturer rather than a lecturer. Next week, week 2 is going to be mainly coming from Ferenc, and he's going to be giving overviews of some of the fundamental tools that sort of enable this revolution in deep learning. Key amongst them, automatic differentiation. So less on the specifics of one individual tool, I think, although we will be focusing on PyTorch for the course. But I think what Ferenc is going to do there is talk about the principles behind automatic differentiation, how it works, why it works, what the sort of problems that come up, and what could go. I think, and Ferenc can correct me in the chat if I'm saying this wrong. So I'm just seeing a question. Is there any way of getting lecture notes in a PowerPoint PDF format to annotate? Yes, you can definitely print a HTML as PDF. That's probably the best suggestion I have. There won't be a for my lectures, there won't be a PowerPoint version. The other lectures, I suspect, may well use PDF and PowerPoint because I'm using Reveal. This is how I'm presenting this. Thanks for the question. So on automatic differentiation and sort of compute graphs and how that works and why that works. And then the lecture 2 of week 2, Ferenc will talk about optimization, stochastic gradient descent. And it turns out it's very, very important how neural networks are being optimized as far as we understand in terms of why they give good generalization performance. And Ferenc will talk about that. Then Nick's going to come in with talking about hardware and sort of how this is all mapping. I mean, basically, the only reason these things run so quickly or are possible is because people are doing clever things with hardware, taking those compute graphs from PyTorch, etc., mapping them onto the hardware. And so Nick's going to talk about that in week 3, the first lecture. And then because it's the first time we've given it, we're sort of fairly convinced that as for the second lecture in week 3, we'll realize a number of things we should have said or didn't say or thought one of us was going to say and haven't. So we're going to use week 3 as a summary and gap filling. And if, of course, we taught everything beautifully, if we believe we did, then we can just use that for a Q&A. So have you ask us questions about the material so far, make sure your understanding is up to speed. Then we'll also set assignment 1, which is going to be 30% of the course. And assignment 1 is going to be on that sort of first underlying ideas about what's caused the deep learning revolution. That is going to be quite a quick turnaround. Now, what's the reason for that quick turnaround? We're looking for that to be submitted week 4. That's because I sensed, just talking to I was director of studies, as Melissa, who's in the audience, knows, for the first time last term. And I noticed how stressed the students started getting around week 5 in terms of that's when all their assignments started coming in. So we thought we'd try and get our first assignment done, make it a shorter assignment and quicker, and have you submit it by week 4 so that you're trying to get it in before things get really busy for you. And I hope that's okay. Of course, we'll welcome feedback about this stuff as we go through. Oh, sorry, I forgot to say what the material was. And across week 4, in terms of the material we'll teach, we have convolutional neural networks, which I'm sure you'll have heard of, one of the sort of mainstays, early performers of neural network revolution. That's going to be covered by Nick and or Ferenc, and recurrent neural networks as the second thing. These are the sort of first 2 deep neural network architectures that were developed, and the first 2 that were sort of used in anger to deliver on the sort of current AI revolution. So we'll be looking at those. And then week 5, we'll shift to what we perceive to be the current state of the art. So although convnets and recurrent neural networks are the traditional approaches, if you see what's going on in the literature now, you'll see attention features very greatly and transformers feature a lot. So we're going to aim to use week 5 to sort of tell you what we think the current state of the art is, and Ferenc will be leading on those. And at the end of week 5, we're going to set the assignment 2, which is the rest of the assignment, and that will be due on the last day of week 8. So what are we going to do across week 6 and 8? Well, we wanted to use the opportunity to sort of talk about sort of what we think of as special topics. So this is either going to be us, or we've got guest speakers. So we've already got Raya Hadsel from DeepMind lined up on the 11th of March to come in and tell you the sort of things that they're doing, either in deep learning or that relate closely to deep learning. So it's a sort of chance for you to hear a bit more about the state of the art. So you can see the nature of the course is what we're trying to do is give you a sense of the fundamentals about what's brought this revolution around, followed by giving you an understanding of what the sort of mainstay methods are/were in terms of the convnets and the recurrent neural networks, how they work, the sort of classic deep learning neural methods. And then what we think is the current, the present, and the future in terms of the methods such as transformers and sequence of attention, how all of that's working. So let me pause there. I can see Ferenc has mentioned that he's going to use HackMD or Google Slides for the content. Let me just stop though and see if there's other questions from people or clarifications on the way we're planning to set things up. That's great. So Akvile is asking what will be the format of the assignments. So we're being slightly reactive in terms of seeing how the material comes together, but our sense is that there'll be short questions. Now, I think Ferenc pointed out when we were discussing the course, a really good point. If we would love to give you sort of mini projects to go away and do something with deep learning, but that's quite problematic because to do some of the more serious things that you might be interested in doing, the amount of compute you need is pretty large. So rather than doing that, we decided that a better idea would be to give you shorter questions, and they'll come, and that also allows us to mix in the material from each of us. So you might end up with sort of 1 or 2 questions from each lecture, which will require you to perhaps do a little bit of coding or perhaps a little bit of maths. And so sort of more tutorial format questions and submit questions on that basis. So we don't have those assignments finished yet because partially, and that's why you should give plenty of feedback as we talk, we'll be reacting to sort of where your understanding is. Yeah, that's so, David, though you can do Google Colab. Yeah, absolutely. But yeah, I guess even with that, you know, my experience with PhD students, and a great way to go, by the way, Google Colab for running experiments, for trying these frameworks. For example, PyTorch is easily installed. You don't have to worry about installing on your machine and all that mess. So I'll definitely be trying to make sure the things I do run in Colab for you. But even those provisions can be not quite enough. But you can imagine it's possible to do things like learn MList and stuff like that quite easily. So, you know, there might be exercises like that. Thanks, David. Okay, so if there's no further questions, I'll sort of move on to, I mean, and this is a personal perspective, and Ferenc and Nick can disagree in the chat, but just to give you the context of what I'm about to say, you know, it's a question like I sometimes get asked. I used to have to tell like executives in Amazon this. I'm sure Nick and Ferenc have had similar experiences. So what is machine learning? Well, this is my sort of universal formula for machine learning, which basically I see it as this. It's the combination of data with models, through compute to make predictions. So what does that mean? Well, data, that's observations. And I think of data very, very generally. So data could be actively or passively acquired. It can even have data about data. You know, or to me, almost anything is data. There's a sense in which in computer science, the term data means something slightly different. I guess traditionally we mean data in the way that statisticians mean data. And what's the model? Well, the model is our assumptions. And those assumptions are typically based on previous experience, other data. Techniques like transfer learning, where you learn from one data set and transfer that understanding to another. Or my favorite thing is beliefs about the regularities of the universe. So how you think the universe operates. So a physics model is some belief about the regularities of the universe. And sometimes in, say, things like cognitive science and psychology, we think of that as inductive bias. Now, the difficulty is, whatever these beliefs we have, we need to be able to combine them with the data in some way through compute. And that can severely limit the type of things we might include in our model. So there may be things that we know that we would love to include in our model, but we don't have really good ways of combining those things that we know with the data in a computational algorithm. And that sort of limits the sort of our freedom to a great extent in the model. So if we think, for example, about climate models are models, but they're models that take supercomputers to run and, months of potential compute time. And they're actually quite difficult to integrate with data on a large scale, but they have an enormous amount of physics. So that tends to be the domain of science to run such simulations. In machine learning, we tend to have simpler assumptions, things like we're going to assume the world is smooth. Like if I were giving this lecture live, I would make a statement about you would be surprised if I were to disappear from the left of the room and reappear on the right of the room, because you have a smoothness assumption about me and the physical world. Given that we're on Zoom, you would be utterly unsurprised if that would happen, because you would just assume that there'd been a delay in the transmission. And the prediction is the classic focus of machine learning. So you can look at model and data and try and deal with that in different ways. You can try and use the model to understand the universe better, or to make a better decision about an intervention. And that would be causal sort of learning, which is typically the domain of economists and some branches of statistics, but is increasingly the domain of machine learning as well. So Ferencz is very interested in causal machine learning. But the traditional approach of machine learning was not to worry so much about the interpretability of the model, just to try and get a good prediction out. So it differs in that sense from statistics, where the focus is typically on what am I going to be able to say about this data given this model after I've done the analysis. Whereas, and you might be interested in that because you're trying to understand a disease like COVID and why certain people are getting COVID in certain regions. You want an explanation. In machine learning, the traditional focus was on prediction. Okay, so to do that, we need two things which are key. Not all machine learning algorithms have these two things. One, what I think of as a prediction function. Now, in deep learning, the prediction step is very, to my mind, confusingly called inference. That's what it's called, so I have to accept that. But prediction function is the inference function, the sort of forward prediction about here's some input and here's what I think is going to happen, which includes smoothness or something like that. And then you have an objective function, and the objective function or cost function or error function, that defines the cost of a misprediction. You typically fit your prediction function with your objective function. Now that's the general approach. So what's that got to do with deep learning? Well, it turns out that at some level, deep learning is providing us with particular prediction functions that allow us to focus on particular data types like sequence data or image data, and give us performance in making those predictions that put them well ahead of other classes of techniques. And that's really, to my mind, what's been driving their success. So for the rest of this session, I want to sort of give you the sort of historical context for sort of how we got here, because I think it helps in understanding that this general framework that I've spoken about, there's many parts to it. And one of the things I want you to go away with is an understanding of when and how you should be using deep neural networks. It is not a panacea. It's not the right solution in every occasion, but it's really very effective in many occasions that we're using it now. And sort of to help tell that story, I like to give you a narrative. And the narrative in this case is going to be a historical narrative. And I like all historical narratives. I wasn't there for every moment of this. So it's potentially up for debate, but it's the one as best I understand it. So I'm going to take you all the way back to what I see as the origin of machine learning, and certainly the origin of neural networks, which is this field of cybernetics. Today, we keep talking about machine learning as artificial intelligence, but artificial intelligence was first used in 1956 as a term, and it was almost explicitly used in an effort to separate from the cyberneticists who date back to the sort of late 1940s. And so it's a very misleading term because the field went in a very different direction after AI came in. But the origin of the field really goes back to these people who are sort of somehow very cool looking. So on the left, you should presumably recognize Bertrand Russell. On the far right, there's Warren McCulloch. And in the middle is the right of the three, there's three figures because there's a frog, is a guy called Walter Pitts. Now, there's a fantastic story that Walter Pitts, when he was 12 years old in 1935, he got a copy in his local library of Bertrand Russell's Principia Mathematica. And this is a 12-year-old, let's be very clear here. And he read it and he thought he found some mistakes. If you've not looked at Principia Mathematica, have a look at it. I can't remember, Russell was very proud of the number of pages it takes to get to proving 1 + 1 = 2. So it's Russell and Whitehead. So he believed he found some mistakes. So he wrote a letter to Bertrand Russell, 1935. And Russell wrote back saying, wonderful, you should come and continue your education with me here when Pitts was 12. So Pitts did not go. But what did happen is 3 years later in 38, Russell went and sort of spent a sabbatical in University of Chicago. And Walter Pitts was 15 by then, and he just went to Chicago to listen to the lecture series that is a very famous lecture series, because Rudolf Carnap was there as well, that Russell gave. And then sort of Pitts just sort of hung around University of Chicago. He didn't take a degree. He he hung around sort of Rudolf Carnap, another philosopher of logic, until the gentleman on the right showed up, who was quite a lot older, 15 years older than Pitts. That's Warren McCulloch. McCulloch was a psychologist who came to Chicago in 1941. So it's interesting here because Pitts was too young to fight it or be involved in the Second World War in terms of the mathematical effort, which many famous scientists were. McCulloch was a psychologist, so wasn't necessarily relevant to that effort, which sort of explains why in 1941 the two of them met, or I think it was 41. It's in the notes at any rate. And McCulloch was a very generous person and found this sort of person carrying out this itinerant lifestyle and said, look, just come and live with me and the family. And they wrote a paper which was the first paper with a model of the neuron. And that's known as the McCulloch-Pitts neuron. But the interesting thing about that paper is it's almost entirely an effort to explain how the brain does logical reasoning through those neurons. So it's very distinct and different from what we would think of as a modern neural network. And this separation between logic and the sort of machine learning or the connectionist approach is something that is like a strand through the story of AI and cybernetics going back to the late 1940s. Bear in mind, this paper is predating all the work on digital computers that we're very familiar with today, like the von Neumann paper, which led to the von Neumann architecture, or work from Turing, etc., or even sort of papers that talk about NAND gates as universal gates. So what they were trying to do in this paper was show that the neuron through this model was a universal gate. Now, that was considered very interesting work, particularly by the person on the right here, who is Norbert Wiener. So Norbert Wiener wrote a book in 1948. He was involved in the Second World War in radar systems. He also was a child prodigy, and he visited Russell at the age of 19, having got a PhD from Harvard, to also understand logic. But he really did not like logic. He's got this wonderful quote where, because logic was the prevailing theory at the time, the theory of knowledge. What Wiener said is, we don't need a theory of knowledge, we need a theory of ignorance. And the reason I've shown these other two gentlemen here is James Clerk Maxwell and Josiah Willard Gibbs, because Wiener picked up on their study of statistical mechanics, the use of probability to represent the unknown in small-scale physical systems as the right route for understanding ignorance. And indeed, Shannon picked all that up from Wiener. So Shannon spent a lot of time talking to Wiener when he developed information theory. So Wiener is the sort of person who tried to move away from logic and towards, say, probabilistic representations, but also wrote this book which covered the whole lot, said, look, we need to look at animal intelligence, etc., etc. And this book is called Cybernetics, and it carried people like McCulloch and Pitts with it. Now, the next person in this story I want to introduce was actually based in the UK. So this is a gentleman called Donald Mackay. Donald Mackay was working, as well as Wiener, like Wiener, was working on radar during the Second World War and helped in building systems that tracked, I think in his case, ships, although Wiener was working on aircraft. Now, the interesting thing about these systems is that when they built these tracking systems, they used techniques that Wiener developed, such as the Wiener filter, very closely related to Gaussian processes. In fact, they are Gaussian processes, to try and track aircraft. Aircraft in particular, difficult, and also ships. By the time the bullet, or whatever it's called, the artillery shell gets there, the ship or the aircraft has moved. So you're trying to track to where it will be. And they built systems for doing this that actually were highly accurate and were used like until the 1970s at MIT and Bell Labs, and Wiener was involved in that. Mackay involved in the same thing for ships. But the key point about Mackay is he became an academic after the war. He actually wrote this book called Behind the Eye, which is his Gifford lectures. He became very interested in the brain. He joined the British version of the cybernetics community, which was known as the Ratio Club, spelt ratio, but for some reason pronounced ratio. And what all these people were interested in was how they could emulate intelligent type actions. And my favorite quote from, see if I can find it in the page, from Mackay on this is from 1986 Gifford lectures. He unfortunately died shortly after the lectures, but he talks about how he got into the brain. He says, so in a chapter titled What Are Brains For? Working on radar, and I found myself drawn into brain research afterwards, partly because during the war I had worked on the theory of automata and electronic computing, and on the theory of information, all of which are highly relevant to things such as automatic pilots and automatic gun direction. These are tasks that had formerly required human operators. Were there any limits, we ask ourselves, to the artificial simulation, eventual replacement of human beings in roles hitherto regarded as cognitive and intelligence? Now, what he goes on to say in that quote is the difference between the analog and the digital, and the analog and the digital computer. Because after the war, there was the rise of the digital computer, but all of these systems that Mackay and Wiener had built were analog systems. What do we mean by analog systems? What we mean is that they could write down a mathematical representation of how the ship or the plane was moving. They could then turn those differential equations into a set of electronic components, analog electronic components, resistor, inductor, capacitors, which they then used to build a representation of what that object was doing within the gun. So the gun had a model of what was going on in the outside world, but the model itself is a set of analog electronic components. That's why it's an analog, because each of those components is in some way analogous to something in the real world. It's not because it's continuously moving, it's because it's an analog, analogous to something in the real world. Now, the thing about the digital machine is at the heart of the digital machine that we all study and know and love, which was only being developed sort of in the Second World War, as we know, ENIAC, EDSAC, Colossus, etc., is at the heart of the digital machine, there is an analogy that allows you to create a logical gate, that allows you to create logical truth tables, that allows you to do all the work that's laid out in Principia Mathematica. So there's a route to doing maths that has an analogy that gives you logic. But that was too slow. So a lot of what people were doing were using analogies that gave you the maths directly. And that's the difference between analog and digital. And you wonder, why have I belabored that point? Well, because it's a major reason why neural networks sort of faded for a while. Who we have on the right is Frank Rosenblatt, and he was inspired to create the first sort of what could be seen as a deep neural network, although only one layer was adaptive in the network, by papers by a guy called W. Ross Ashby, who was a British cyberneticist and very inspirational for many cyberneticists, including von Neumann, who was not a cyberneticist, but who was also involved and wrote papers on how you could combine probabilistic decision systems to make a single entity. And that's what led Frank Rosenblatt to create the perceptron. But poor old Frank, he was living in the analog world. So the way that you could do that maths, you had to build electronic components that were giving you the analogy to the maths you wanted to create. Digital computers were not fast enough. This is sort of all happening in the late 50s into the early 60s. And at a very, very similar time, the Dartmouth Conference is launched, led by John McCarthy. Now, the thing I think about that conference is it has very little to do with machine learning. Neural networks are mentioned once in that proposal. Cybernetics is not mentioned at all, and the work of Wiener is not mentioned at all. Unfortunately, John von Neumann was dying by the time that conference was on. Alan Turing was already dead. Ross Ashby was in the United States, but he was not invited. It basically was arguably a new group of young bucks that wanted nothing to do with this older generation. So they went in a different direction. There were also personal animosities by this time between McCulloch and Wiener and various other things. So there's all sorts of reasons why AI split off, and I could give you all the narrative for those different reasons. But fundamentally, there's a technological reason as well. I mean, people can fall out, people can die, but if the technology is going to work, then you're going to have to stick with the old technology. So there's lovely stories, I mean, lovely stories, horrible stories about what went on between different people and how you shouldn't treat people when you're an academic, that you could learn a lot from. But fundamentally, the reason the AI field, the Dartmouth Conference, came to dominate was because of the increasing speed of the digital computer. So there was this period between, let's say 1962 and let's say the early 1980s, where the computer was getting much, much faster all the time. And it seemed possible that the challenges of artificial intelligence could be solved through programming, and the computer was just going to get faster. And it was just with faster computers that we were going to resolve the challenges we faced in terms of the fact that it was difficult to program computers to recognize objects, et cetera, et cetera. But by the mid-80s, so this is basically the first neural network winter. There's 3 waves of neural networks, and this is the end of the first. It sort of ends with Rosenblatt. There's a lot of interest in neural networks up until this period, the sort of early 60s. And then you go into this sort of the dawn of classical AI. But that only goes on until the mid-1980s. And what happens at that point is sort of AI sort of fails to deliver. So there's a lot of hype, like there's been around machine learning, around what AI is going to do, but you can't even build computers that can do simple things such as recognize the people in this image. And this image is from the first connectionist summer school, which was in 1986. This group of people, by the way, were made fun of by the real AI people. I did a Talking Machines episode with Terry Sejnowski, who's sitting on the front. He's not the furthest to the right, he's second to the right. He's next to Jeff Hinton, who's all in black there, looking very Steve Jobs-like. They used to make fun of this group, the sort of classical AI people, because they're wondering, what on earth are you doing with your connectionist models? But this is really the second wave of neural networks, and it was triggered by this group of people who talked about these methods. Mike Jordan's also in there. So look, this is Mike Jordan. That's Jeff Hinton. That's Terry Sejnowski. This is Richard Durbin, who moved, and quite a few people in early machine learning moved into computational biology. So he's very well known. He's a professor in the University of Computational Biology. There's other people who are still around the community here, like Mike Moser. Jan LeCun is there. So there's a bunch of sort of interesting people in this picture, and not that many. I'm not on the scene by this time. I'm only 14 years old. And they launched this book called Parallel Distributed Processing, which I have a copy of here, which actually laid out a set of algorithms that actually worked. And that's the sort of second wave of neural networks. And you know, the reason things start to work because you start to get machines that are capable of running these algorithms, machines like the Sun 4, which was used for the first convolutional neural network paper. So this is the volume 1 of neural computation. So what an active community. They're producing their own journals. They're starting their own conferences. Europe's conference started in about 1986. And this journal here has the paper from Jan and his collaborators, details in the notes, where they trained a neural network on the US Postal Service data set of handwritten digits. Now, this is not the MNIST set that is quite famous. This is the USPS set, which is 7,291 digits. And the first convolutional neural network was able to get down to an error rate of 5%. Error, which was considered good at the time, and it's a difficult data set. I think humans do 2.6% on this data set because the test set has some unusual examples in it. So that was kind of considered a big breakthrough at the time, and you know, big enough that it was on the cover of the main journal representing this field of people known as the connectionists. Now, what happened to that? Well, what happened to the second wave? Well, I think I'll probably skip through these and just sort of talk about this section rather than saying about it just in the interest of time. Well, what happened was we were using techniques to build prediction functions and combining them with objective functions. And when you sat back and look at what we were doing from a mathematical perspective, it turned out that there were more elegant techniques that were mathematically easier to analyze that gave you equivalent performance. So this is kind of oddly where I enter the scene. So like 1995, I was working on oil rigs and I had a laptop and a copy of Ball and C++, and I was sitting there trying to code up neural networks. By 1997, I was doing a PhD at a place called Aston University. I wasn't actually at Cambridge at the time. And this is my first visit to Cambridge. This is a picture of me. And this is the days before digital. So this is an analog camera that I put on a little tripod. This is Clarkson Road. And you can see the Newton Institute in the background. And what you do not see is any other mathematical buildings because there was just wasteland around it. And we had this machine learning and generalization summer school in 1997, which I was very lucky to go to, 2nd of August, 1997. And it was my first sort of trip to Cambridge to do anything in machine learning. And it was just a who's who of machine learning was there. Jan LeCun was there, Vladimir Vapnik, David Mackay, Jeff Hinton. I mean, it was just an amazing conference, 120 people. It was like a core of this connectionist community came together to discuss generalization. And I was just totally in awe because we saw this for the first time. This was a net 5. Jan LeCun's convolutional neural network being trained on MNIST data, and I think it was down to an error rate of less than 1% on these digits. And it wasn't just amazing, the performance of this thing, but just to give you a context of the time, it was amazing that someone was giving a presentation through a data projector, right? You know, most people didn't have that. You gave presentations on overhead transparencies. So I remember being in awe of Anne's presentation. He had music going in the background as he showed these sort of videos. But the important thing he was able to do, and by this time, this is 1997, so of course computers got faster, his neural networks got bigger, is he can train these neural networks to deal with some of these invariances in the data. And you know, that's the idea that certainly translation invariance is being encoded in those convolutions. There's a lot of weight sharing, and you can see he's got all these visualizations of the weights on the left-hand side. Here's the same for scale invariance. But oddly, this amazing thing, which I was absolutely stunned by because I'd come to do neural networks and I was just thought this was like the coolest thing ever, was very rapidly faded. And it faded because of work by these three. So the support vector machine, this is Karina Cortez on the left, who wrote the paper Support Vector Networks with Vladimir Vapnik on the right, which gave the sort of first practical implementations of support vector machines, and Isabelle Guillon in the middle, who with Bernard Boza and Vladimir Vapnik wrote the sort of first paper on practical algorithms for large margins. Now, there were other techniques like graphical models, Gaussian processes, et cetera, that came into the community then. But basically, the community switched from these mathematically tricky objects, neural networks. They're algorithmically easy, but the maths of understanding how they work is hard, to mathematically clean models that were easier to understand. And it wasn't just because we wanted to play with elegant maths, it was because these models performed better. So if you look at something like MNIST, the support vector machine was able to get pretty much the same performance on that data set as this very complex LeNet 5. And that meant that the community switched for sort of about the next sort of 10 or 15 years away from these deep neural network techniques, which have this amazing ability to learn the features. So what's going on, what Jan would say, and what Jan has always said back to 1989, on the left here, is it's a bunch of feature detectors that are learned. And that's the amazing thing about deep learning. Those feature detectors are not being designed, they are being learned from the data. And I'd argue that that's still sort of the power of the method today. But what has changed since then? Well, a few things. I like this in Jan's paper. This is 1989, the convolutional neural network. So they wrote their own little neural network software, and for writing their convolutional neural network, him and Leon Botu, who's still around in the community and doing great work. This work points out the necessity of having flexible neural design software tools that ease the design of complex specialized network architectures. This has been critical in the deep learning revolution, having software that allows you to build these complex systems, which are compositions of simpler neural networks together, such that you can get the type of training performance you need. Next, these two, Olga Rysakovsky and Fei-Fei Li. So Fei-Fei was a PhD student at Caltech with Pietro Petrona, who had done a lot of work building data sets. And when she graduated, she really believed in the idea that we need a massive data set. So ImageNet, there's an enormous amount of work to collect, driven by Olga and Fei-Fei, this enormous database of millions of images. It wasn't until we got to that size of data set that we start seeing the massive improvement in performance that you get from neural networks over other techniques. And of course, there's the famous AlexNet 2012 was deployed and basically revolutionized computer vision. And we've seen similar things in speech, like when you get to large enough data and language, we're seeing the same thing today with transformers. And we're seeing a lot of work trying to create artificial data sets from simulations in order to provide the quantity of data that these models need. So the third wave of machine learning neural networks is reliant on these things. Data, many classes was something Ferenc was pointing out when we were talking about this. It's not just about large data. There were thousands of classes in ImageNet as well. So how we handle that, doing that with neural networks is key. Compute, being able to use GPUs, but increasingly people are designing specific hardware for running the inference of these things when they're deployed. You know, mobile phones contain chips now that will run neural networks. So even if it turns out, what does that mean? That means even if it turns out that they were a bad idea, whatever your good idea is, that's better, you're going to have to work out how it can be implemented as a neural network to deploy it on a mobile phone, because the mobile phone will only deploy a neural network efficiently. So whatever we think in the future, we are stuck with neural networks now, just as we're like stuck with certain approaches for doing graphics because of the designs of chips or designs of OpenGL or whatever else. Stochastic gradient descent, absolutely vital in terms of fitting these things at scale, and why does that work? And of course, I mentioned already the software and AutoGrad. And these dominant domains of use in sort of speech, vision, language, often the domains of human perception. And it's sort of interesting that that keeps coming up. And I think there's multiple reasons for that. One, because they're kind of harder domains, but two, because getting such large quantities of data, you need tasks that humans can perform quickly to acquire the data. There's a number of other things which sort of fit in around the edges, that things like unsupervised pre-training, which enable these methods to work initially, but we don't seem to need anymore. The use of ReLUs for getting around practical issues around gradients. The fact that now there's a zoo of methods and models and you can just pick amongst them to try and get the thing going. And then what we're going to talk about next week is try and give you some instinct for why they generalize well. So what's the course going to be about? Understanding the principles behind generalization, optimization, and implementation, in particular on hardware, and then giving you an overview of the different, with a T, neural network architectures. And I'm going to stop the recording there and give you a chance to ask some questions.